Okay, this says that Karen rides her bicycle along a straight road from home to school. So she's going forwards and backwards, starting at home at time 0 minutes, and she arrives at school 12 minutes later. During that time interval, this graph represents her velocity in miles per minute, and it's basically a piecewise function. It's just a bunch of lines. Okay, first question says find the acceleration of the particle at time t equals 7.5 minutes. So remember we learned that the acceleration is the derivative of the velocity graph. So if this is your velocity graph, the acceleration would just be the slope of this graph. So I want to know what happens at 7.5, which is right there. So I need to find the slope of that line. So the acceleration at 7.5, if you do change in y, would be negative 0.1. I'm going down by 0.1 and then to the right 1. So you can say negative 1/10. Units would be miles per minute squared, right? The units on top is your velocity unit, which is miles per minute, and then you're dividing by the time again, which is minutes. So that's part A. Okay, part B, explain the meaning of the integral of the absolute value of the velocity function for Karen's trip. And then we're going to actually find that value. So in part B, what we're doing is, because we're taking the absolute value, we're going to find the area of all of these pieces, but we want to count this as also to be positive. So if I do area of a triangle for this piece, this area is 0.2. This piece right here is also 0.2. So I got 0.2 there. I'm going to break this up into into triangles, trapezoids, etc. And I broke it up this way. So you can check for yourself, but this area was 0.15. This ended up being 0.3. This ended up being 0.25. And then 0.6. This is 0.1 right here. So I want all the positive pieces. So this piece down here, even though it's below the x-axis, I want to count it as positive 0.2. So if you do that and add up all the values, you should get 1.8. And the units would on this be, this is miles per minute. You're multiplying by minutes, so the minutes cancel, so really this is miles. So that's the value of the definite integral. And what this represents, this is really the total distance traveled by Karen in miles that Karen rode during t equals 0 to 12 minutes. So that's the interpretation. Okay, part C. After leaving home, Karen realizes she left her calculus homework at home and she returns to get it. At what time does she turn around to go back home? So looking at the graph, remember, movement is given by the velocity function. So basically, when velocity is positive, we're only talking about her moving along a straight line, so going right and left. When the velocity is positive, it means that from 0 to 2 minutes, she was going right. And then when that velocity graph is negative, that means she's going backwards, the other direction, she's going left. So at t equals 2 is when she changes direction. And your reason is, you always justify based on what you're given. It's because the velocity changes from positive to negative. Or you could say velocity changes signs, and that would be fine as well. Okay, lastly, part D. Larry also rides his bicycle along a straight road from home to school in 12 minutes. But his velocity is given by this equation, where WT is miles per minute. Who lives closer to school, Karen or Larry? So we would need to figure out what's their distance from home. So if you think about Karen and her graph, this and this, right, would cancel out because this is her distance traveled forward, this is her distance traveled backwards. So this area here would really represent the distance that Karen lives away from the school. So for Karen, this would represent that distance, and that's going to give me 1.4 if you add up those areas. For Larry, I have an equation, so I'm going to go ahead and integrate this using your calculator. If you go ahead and do that, you end up with 1.6. So based on these answers, Karen lives closer to school. And then this is